Hey everyone, and welcome. Today we're going to tackle a problem that every single student knows all too well. How in the world do you figure out the right order to take your classes when everything seems to depend on everything else? Let's untangle this thing.
You know this feeling, right? If you're in college, you've been there. The course catalog looks like this impossible web of arrows and requirements. You need Chem 101 for organic chem, which you then need for biochem, and one wrong move could seriously delay your graduation. It's a classic prerequisite maze, but it turns out there's a really powerful algorithm designed to solve it perfectly.
And you know, this isn't just about class schedules. This is a fundamental challenge of ordering tasks. I mean, think about building software, managing a project, or even just following a recipe. Anytime you've got a list of things to do, and some of those tasks have to be finished before others can even begin, you're looking at this exact same puzzle.
So the fundamental question is, how do we find a straight line, a single valid sequence through this tangled mess of dependencies? How do we take that chaotic map and turn it into a simple step-by-step checklist that guarantees we do everything in exactly the right order?
Well, the solution has this fantastic name, topological sorting. And I know it sounds way more complicated than it actually is. It's basically a method, an algorithm, that is tailor-made to take a set of dependent tasks and just spit out a valid order for completing them. It's our hero for today.
Okay, so here's the formal definition. But all it's really saying is that if Course U is a prerequisite for Course V, then in our final plan, Course U has to show up before Course V. That's it. It's just an algorithm that respects the rules of the game. But for it to work its magic, it needs a special kind of map.
And that map is called a directed acyclic graph, or a DAG for short. Let's break that down. Directed just means the relationships are one-way streets. Course A leads to B, but B doesn't lead back to A. And acyclic, well, this is the most important part. It means there are absolutely no loops. No situations where you can follow the arrows and end up back where you started. A cycle would be like needing class A for B, B for C, and C for A. That's a problem.
And this shows you perfectly why those cycles are a total deal breaker. On the left, you've got that impossible prerequisite loop. To take A, you need C, but to take C, you need B, and to take B, you need A. You can never, ever start. It's impossible. But on the right, we've got a DAG, a nice, valid chain. Now that is a problem we can actually solve.
So how do we solve it? Well, our first method is called Kahn's algorithm. I kind of like to think of this as the common sense approach. It works by finding all the possible starting points, the classes with no prerequisites, and then just systematically working its way forward from there.
The logic is super intuitive, really. First, we just count how many prerequisites each course has. That's its in degree. Now, any course with an in degree of 0 can be taken right away, right? So we add all of those to a queue. Then, we just start processing that queue. We take a course, add it to our final schedule, and then go to all the courses that needed it and tell them, hey, one of your prereqs is now done. When a course suddenly has all of its prerequisites met, its in degree becomes 0, and boom, it gets added to the queue. We just do this over and over until every class is scheduled.
All right, let's see this thing in action. Here's our little sample of courses and their dependencies. So first, we calculate the in degrees. And as you can see, courses 4 and 5 both have an in degree of 0. They don't depend on a single thing. So those are our starting points.
And because there are starting points, courses 4 and 5 become the very first items in our processing queue. This is the starting line. Okay, let's start processing. First, we pull course 4 out of the queue and add it to our final schedule. Now, course 4 was a prerequisite for courses 0 and 1, so we go and tell them. Then we process course 5. It was a prereq for courses 0 and 2. After both 4 and 5 are done, something cool happens. Course 0 has now had both its prereqs met, so its in degree drops to 0. Same for course 2. They're now eligible to be taken, so they get added to our queue.
And the process just keeps going. With 4 and 5 on our schedule, we can now pull course 2 from the queue. And when we complete course 2, that satisfies the prerequisite for course 3, which now has an in degree of 0, and you guessed it, it gets added to the queue. It's like a chain reaction, just systematically unlocking one course after another.
And after we run through the entire queue, this is what we get. A perfectly valid sequence of courses. If you followed this plan, you'd meet every single prerequisite right on time. We've literally turned chaos into a clear, actionable plan.
But Kahn's algorithm isn't the only way to crack this nut. There's another approach that kind of thinks about the problem backwards, using a concept called depth-first search, or DFS. Instead of a queue, this one uses a stack. So the idea here is to kind of work backwards. We start at any course, and we just explore its prerequisites as deep as we can.
Once we hit a course that has all of its own prerequisites already visited and processed, we consider it finished and push it onto a stack. Think of it like putting the last task you do at the very bottom of a pile. We keep doing this until every single course is on the stack. Then, to get our final schedule, we just pop them off the top of that pile. So after the whole DFS process has explored all the paths, we're left with a stack of our finished courses. The courses that were finished first, the final steps in any chain, are way down at the bottom. The courses that were finished last are sitting right on top, ready to be popped off first.
And now, we just empty the stack. Popping them off one by one gives us this order: 4, then 0, then 5, 2, 3, and 1. Now, notice something? This is a different order from the one Kahn's algorithm gave us, but it's still 100% valid. And this shows a really key insight. For a lot of these puzzles, there isn't just one right answer. Having multiple valid schedules gives you flexibility when you're planning your semester around work or clubs or, just sleeping in.
So this is way more than just a neat computer science trick. Understanding topological sorting is kind of like having a superpower for organizing complex projects, and it shows up in some incredibly important places you might not even realize.
Yeah, we've been focused on course planning, but this is the exact logic that software build systems use to compile code in the right order. It's what project management tools use to map out these crazy complex timelines. It's even happening deep inside your computer's operating system as we speak. It is the fundamental pattern for getting things done right.
Ultimately, it all comes back to this one simple, powerful rule. Whether you're using a queue or a stack, whether you're planning a semester or building an app, the goal is always to respect the dependencies. You just have to make sure that for every task U that must come before V, well, it does.
So the next time you're facing a tangled mess of tasks, try thinking about it like a graph. Find the one-way streets, identify your starting points, and I bet you'll find your path. So what other complex systems in your life could you untangle with this? Thanks for tuning in.